Now, as you can see from the title on the screen, Series and Induction, we're going to talk about some slightly new topics. And I say slightly because we've already talked about geometric sequences. The first thing we'll talk about here is a geometric series and their infinite sums. So series will need to be defined, but you'll find out that the geometric sequence, as I said before, has great importance in mathematics, and we will see some of that now. So here's the definition. Let's go ahead and do this right away. Definition: the expression which follows here, a plus ar plus ar squared plus, you see what I'm doing? I'm taking the geometric sequence we've seen before, now I'm adding the terms, up to some typical term ark minus 1 plus dot dot dot. We are now going out to infinity, so I don't stop after the nth term. I can also write this in shorthand, of course. Take the typical term here, a times r to the k minus 1 power, and then let the index k go from 1 to infinity. And again, there's infinity showing up to indicate that this sum is the sum of all of these forever. Now let me box this entire object in here. All right, this is the expression we're discussing. Now this expression, and there's some words to go along with it, this is with first term a and common ratio, just like a geometric sequence, common ratio r, of course r is not 0. This is called, here's what we're going to call this, an infinite geometric series. Infinite, of course, geometric series. Now, the word series has come down to us from history. And you might say, why didn't we just call this an infinite geometric sum? Because we're adding things up after all. Well, that's a very good question, and I'm going to give you the reason why we don't do that. We reserve the phrase infinite sum, as opposed to series, for cases, and you'll see, cases when the infinite series, as we have above, the infinite series adds up to a finite real number. So when this actually adds up to a real number, when it doesn't go to infinity, for example, or have some other problem, but when this actually adds up to a number, then we'll say infinite sum. Until that point, and until we know, we'll just call this infinite series. But we won't examine series in general. We are going to limit ourselves strictly to the geometric case here. Okay, what would be that sum? Well, here's the theorem that tells us exactly what that is. In the geometric case, we can actually write down a theorem for this. And here's how it goes. If, and this is a most important if the absolute value of r is less than 1, let me box that in and show you what I mean pictorially. If this is 0, and this is, say, minus 1, and this is 1, we're talking about all the numbers, of course, not including 1 and minus 1, that lie between them on the axis. Okay, so this is where the r comes from. All right? And only there. So if r in absolute value is less than 1, then the infinite geometric series we saw above, the infinite geometric series, a plus ar plus ar squared plus dot 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 up to the typical term ark minus 1 plus dot 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 out to infinity, has a finite sum, and that sum is, using the shorthand, it is the sum of the a times r to the k minus 1s, where k goes from 1 to infinity. So this is just the shorthand version of this longer expression. And here is where the theorem lives, right there, in this equal sign. What does this equal to? It turns out to be equal to a over 1 minus r. The first term over 1 minus the common ratio. And that is what you want to remember from this theorem. When you add up an infinite series like that with this form, and remember to notice here that when k is 1, the first power here is the power 0. Okay, I'll write that in. The power is 0 for r. When that is the case and you're adding this up to infinity, you're going up through all of the values of this geometric sequence. This is what the sum turns out to be. Now this is quite nice, and what I'll do here is I'll give you the proof idea for this, but not a complete proof, because there's a couple of things there we can't do in here. First, however, let me make a warning that has to do with that hypothesis. If it so happens that the absolute value of r is greater than or equal to 1, that is to say not between -1 and 1 on the x-axis, then the formula is false. Then the a over 1 minus r sum formula is false. In that case, in fact, the geometric series may have a sum, but it will be infinite, or it may not have a sum and be undefined. Those are cases we won't examine, but I want you to realize that you have to be careful that the r you have is strictly less than 1 in absolute value. Okay, with that little warning in mind, let me go ahead and give you the proof idea for this result so you can see how this comes about. And what we'll do is, if we're going to talk about an infinite series, let's go ahead and recall first the partial sum, the nth partial sum on the way to being infinite. The nth partial sum was s sub n. Now we had a formula for this. This is a times 1 minus r to the n over 1 minus r. Remember that? That was the nth partial sum formula for a geometric sequence. Now I'm going to do a little algebra here. I'm going to break it up by using the top and multiplying the a through. So I'll have a times 1 there over 1 minus r minus the a times r to the n, a times r to the n over 1 minus r. Okay, so I just did algebra to break this apart. No mystery at this point. Now, you notice that this first part is exactly what the infinite sum turns out to be. So there must be something going on here. Well, of course, as n goes to infinity, then the partial sum approaches the infinite series sum, if there is such a sum. So the s sub n approaches the series sum, if there is such a sum. Okay, because you're just taking the partial sum going further and further out. Now, here is the crucial idea. Since here the absolute value of r is less than 1, that was the major hypothesis I talked about, experience suggests, and this is the part of the proof where I'm resorting to experience and not to exactness here, experience suggests that as the power n goes to infinity, if you take that r to the nth power, the absolute value to the nth power, then that's going to go to 0. Right? Because if we have a number that's smaller than 1 and we take higher and higher powers, like taking 1/2 and taking 1/2 squared, which is 1/4, 1/2 cubed, which is 1/8, etc. If we have a number that's less than 1 and we take higher and higher powers, gets smaller and approaches in the limit here a 0. Hence, knowing that, as n goes to infinity, we can make the following statement, that s sub n, which is that form from above, I'm going to recopy this, a over 1 minus r minus a r to the n, there's that r to the n turning up, 1 minus r to the n is going to 0, so this entire term is going to 0. Well, then where does this go as n goes to infinity? Well, all that's left is this part. So that's a over 1 minus r, and that is what I was trying to show in this proof. So really, the only thing left out of this proof is this little bit here that says, by experience, and we won't worry about that in this course, but you see that the idea is pretty clear. The nth partial sum formula, this part goes away as n goes to infinity, and you end up with this, which I think is quite nice. First of all, I have a classic example. This is another one of those classics. show that the following is true, that 0.9 bar, which you remember is 0.999, etc., going to infinity, we'll show that that's equal to 1. Now, I've done this before, but I've never done it with the geometric series in mind. So here we are with the geometric series. We'll go ahead and show that. Now, this really is a nice example. All right, here's how the proof goes. 0.999 dot 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 is, by definition, what does that mean? That's 9/10ths, 9/100ths, 9/1000ths all added together, etc. So 9/10ths plus 9/100ths plus 9/1000ths plus dot dot dot. Well, I can factor out from there the 9/10ths, say. What am I left with? A 1 here, plus 9 over 10 here, plus 9 over 100 here, but I'm going to write that as 10 squared. As you'll see, that's going to be a good idea, all the way out to infinity. Now, before I go to the next stage, I'm going to observe what I have here in the brackets. What I have there is a geometric series. 1 can be thought of as 9/10ths to the 0, or 9 over 10 to the 0. This is 9 over 10 to the 1, etc. It's a geometric series where the a, the first term, is 1, of course, and that, as I said, is 1 over 10 to the 0. And then r here is 1/10, and it is strictly less than 1. So since that is true, I can use my formula. So this is 9/10ths times, using the formula from the previous page, 1 over 1 minus r, 1 over 1 minus 1/10. The 1 on the top is the a now. So this is the formula from the previous page. Remember, a over 1 minus r. Well, the bottom is 1 minus 1/10. That's 9/10ths. That will cancel with this 9/10ths. And so what are we left with? As you might expect, 1. So there we have the proper proof, finally, that 0.99999 all the way out to infinity actually is the same expression as 1. Now, with this in mind, I will pose a problem to you now. Here is the problem I pose. It looks a little bit different, but it really is the same idea. Show that 0.12, now, so I have two things being repeated. So it's 0.121212 out to infinity. And I'll even tell you what the answer should be. Show that that's equal to 12/99ths. And the key here is to realize what you've got. That's why I've written these little lines underneath. This is 12/100ths. This is 12/10,000ths, etc. Okay, with that in mind, go ahead and try that based on what we just did in the previous example, and I'll be back in a moment. All right, let's see what this turns out to be. Now we had 0.121212 out to infinity, so we had two numbers being repeated like that. And as I told you, you want to think of this as 12 over 100 plus 12 over 10,000. Now it's time to start counting zeros. 2 zeros, 4 zeros, the next one should be 6 zeros. And 6 zeros, of course, is a million. So 12 over a million plus out to infinity. But now I'm going to do exactly what I did in the previous problem. I'll first factor out the 12/100ths. What do I have left here? 1, of course. And here I have 1 over, and I'm taking away 100 as a factor, so that'll leave me with 100, which is 10 squared, plus 1 over 10 to the 4th. This is 6 zeros. 10 to the 6th, and I'm pulling out 2, so that's 10 to the 4th, all the way out to infinity. And again, this is a geometric series here. This is a geometric series. And the a is equal to 1 again, and the r in this case is 1 over 10 squared, which is certainly less than 1 in absolute value. So there are my facts, and so I have 12 over 100, and now I use the formula, which is a, which is 1, minus 1 over, say, 100, rewriting it instead of 10 squared. And that was that a over 1 minus r form, which we applied here. And then what is this? 1 minus 100 on the bottom is 99/100ths, which will flip over because we have 1 over that, so we have 12 100ths times 100 over 99. And the 100s, of course, 100 over 100 is 1, so they cancel. And what are we left with? 12 99ths as predicted. So I hope you got that and that you didn't find it too hard. It's a nice example where the geometric series appears here, and you have to analyze it and use your geometric series sum formula now. Here is another classic example. These are nice to have. Classic, and this one will have a nice picture I can draw with it. Here's the classic. Find the sum, and I will assure you this is geometric, but we'll check if you like. This is the sum of the 1 over 2 to the n powers, where n goes from 1 to infinity. Now that is 1/2 plus 1/4 plus 1/8 plus dot dot dot. We want to find that sum. Okay. The first thing is we'll recognize that it's geometric, but let's go ahead and write down what the a and the r are. So here, a is equal to 1/2. A is always easy, it's just the first term. R, however, we need to calculate using the nth term, just to be sure. So this is 1 over 2 to the n plus 1, all over 1 over 2 to the n. Remember putting an plus 1 over an. Well, the top simply has one more factor of 1/2 than the bottom, so this, of course, is 1/2. And that certainly is less than 1, so we have a geometric sequence that generates this geometric series. So, with that in mind, the series here, 1 over 2 to the n equal 1 to infinity, I need to put in a form that I can use, which means I need to distinguish the a here from the power of r. So I will rewrite this sum as 1/2 times 1 over 2 to the n minus 1. So n equals 1 to infinity. So the first power of r here is 0. And that, remember, what was required for the formula. So with that in mind, this becomes very simply 1/2 times, well, let me write it this way to make it look just like the formula. We're going to apply the a over 1 minus r formula here. So let me write it exactly that way. I was going to put the a out front, but let me put it on top first. So the a is 1/2 on top, and on the bottom we have 1 minus 1/2, which is what r is. Well, 1 minus 1/2 is 1/2. 1/2 over 1/2 is 1. So I've now found the answer to the question. What does this add up to? It adds up to 1. But I want to show you a picture that goes with this, which makes this even more visual. And this is a very nice picture here. I'll even say that. Nice picture. And here's what I'm going to do. Write down a square of area 1. So that is going to mean the side here is length 1, and the side on the top is also of length 1. And so that has area 1. That square is equal to a square of the same size, but I will break it up differently. Again, this has 1, its unit length on each side. But inside, I will first cut it in half. Now this part has area 1/2. Then I will cut the other part in half. This part has area 1/4. Continue this process. This part has area 1/8. This part has area 1/16. And then I continue the breaking up into halves all the way out to infinity. And that simply is saying add up all the powers of 1/2 from n equal 1, which is 1/2, to infinity. And that's what we just proved using our formula for the geometric series. But you can see here that you can see it geometrically also, which is nice since it's a geometric series. 1 is equal to the sum of 1/2, 1/4, 1/8, 1/16, 1/32, etc. out to infinity. So I find that very pleasing. I hope you did too. All right. Here is a problem I will pose to you so you can practice with your geometric series. It's another classic. And here it is. Suppose a ball is dropped from a height of, say, 30 feet. Each time it bounces back up, it rises to 0.8, That's 8/10 of the previous height. Here are the questions we want to answer. What height will it rise to after its third bounce? And what is the total distance the ball will travel if it bounces out to infinity? Of course, real balls can't do that, but we'll assume this is a mathematical ball, and we'll ask what is the total distance the ball will travel. So you give that a try, and I'll be back in a couple of minutes. As we start this problem with the bouncing ball, my first recommendation is draw a good sketch. Sometimes this may not happen immediately. You may have to draw a couple of sketches and fool around a bit to organize them in a way that's clear. Here is what I consider a good sketch. Let us say that this is the floor or the ground on which this is bouncing, and that my initial height here is 30 feet, where the ball is. Now, the ball possibly is going straight up and down, but I can't see that. If I draw a line straight up and down and I continue my bounces, it'll just be one long line that's covered over and over. So what I'm going to do for the sake of the drawing and the sake of the idea is I'm going to spread it out. And I'm not going to try to mimic the actual path of the ball, which is little parabolic paths as the ball may bounce from side to side. I'm simply going to produce a structure here that will help me intellectually, with my mind, see what's going on. So that would be down, and then it will go back up some level, which is smaller than the original, and the next one will go smaller still, and the next one will continue, and that will go on forever. Now, let's label some things here. Down here, I can mark the bounces. This is the first bounce. This is the second bounce. This is the third bounce, which I'll box in because we had a question about that. Now, how long are these lengths? Well, the first one coming down is 30 because the ball is dropped from a height of 30. Now, how much does it go back up? Well, it goes back up 8/10 of 30. That's what we said in the original problem. So 30 times 8/10 is this distance. Well, of course, if it goes up that distance, then it falls back down the same distance. So that distance is repeated. Then what is this distance? Well, it's 8/10 of the previous one. Well, if I multiply this by 8/10, I get an 8/10 squared. So now I have 30 times 8/10 squared being this distance, and of course when it goes back down, it's also that distance. Likewise, the next one will be 30 times 0.8 cubed for that one, and the other side, and continuing on out to infinity. Okay? So now I've set the problem up in the way that I wanted to answer the questions. Now I can begin to answer the questions based on this picture, which I'll keep handy here. Okay, question A. The question, let me bring back the question here so you remember. The question was, what height will it rise to after its third bounce? Well, with the picture we've drawn, the answer is immediate, isn't it? Here's the third bounce, here's the height it rises to, and that's 30 times 0.8 cubed. So the answer is 30 times 0.8 cubed, and that happens to be 15.36 feet. Now see, with a really good sketch like that, some questions are immediate. They come right out of the sketch. Now as for the total distance, that will take us a little more effort. Total distance. Well, let's just write it out before we try simplifying anything. Just get everything on paper and then we'll work it out to see if we can simplify. First of all, there's that distance it drops at first, which is 30. Then looking back to our bouncing picture here, it goes back up 30.8 and then comes back down 30.8. So this number is repeated twice, as is the next one and the next one all the way out to infinity. So that is an insight we get from the drawing. So we will have 2 times 30 times 0.8 plus 2 times 30 times 0.8 squared plus 2 times 30.8 cubed plus ... out to infinity. Okay, well, let's start to analyze this. Now, when you're doing a problem like this, the entire series may not be geometric and it may not follow a nice formula. Sometimes you need to take part of it out from the front and leave that separate. Here I'm going to leave the 30 alone. The rest of it, however, has a nice pattern. I notice that I can factor out from the rest 2 times 30 times 0.8, sorry. Well, I get 1 from this first term plus what's left here, 0.8, plus what's left here, 0.8 quantity squared, plus dot, dot, dot out to infinity. Well, what I have here now is a geometric series. In fact, let me write that down. This is a geometric series, which is what I was hoping for after all. Here a is equal to 1, the very first term, and r is equal to 0.8, which is certainly less than 1. So since this is true, I can use my sum formula, and so this is now 30 plus, what do I have out front here? Well, that I can rewrite as 60 times 0.8. I'm leaving the 0.8 for a reason. And then the formula says this should be a, which is 1 in this case, over 1 minus r, which is 0.8. Well, that becomes 30 plus 60 times what? Well, 1 minus 0.8 is 0.2. 0.2 into 0.8 is 4. So I have 30 plus 60 times 4. 60 times 4 is 240, plus 30 is 270 feet. And that's how far the ball will bounce if we allow this mathematical ball to bounce out to infinity. So I hope you enjoyed these examples and that you practice with geometric series. And when we finish this, we'll come back and talk about another topic entirely called mathematical induction. Now we have a new topic, the other part of the title that's at the top of the page, induction. We're going to talk about a very important mathematical principle of proof. It's called the principle of mathematical induction. And it's not only important in mathematics, it's also important in areas like computer science, as those of you that study that will see. And here's how it goes. Before I state it, let me give you an idea of what it's about. What it is a method. The principle of mathematical induction is a method for proving. Okay, it's a proof method. So proving that a given statement that you may have, a given statement, and it's a statement involving natural numbers. So natural numbers like 1, 2, 3, etc. So a method for proving that a given statement involving natural numbers is true, not only for a few numbers, but for all of n, the natural number set, which is the set again 1, 2, 3, 4, up to typical position n, out to infinity. That's what the principle of mathematical induction is about. Okay? Why is this useful? Well, it's useful because I can't count to infinity, and neither can you. So if I want to prove a statement involving all natural numbers is true for all n, I can't count, I can't actually try it for all infinite number of numbers. So we can't actually check an infinite number of cases. So we use this technique to avoid that problem, infinite number of cases. Okay? So, let me show you the kinds of things that mathematical induction is good for. Here are some examples of some statements. So let me go ahead and write down some examples of such statements. Okay, and these are all going to be true for all n in the natural numbers, but to prove that they're true, I will use the technique of mathematical induction. Now these are simple ones, but they'll, I hope, point out the value of this. Number one, statement number one. Let's say you want to add up all of the odd numbers up to a certain odd number, 2n minus 1. Well, it turns out that that is just n squared. The first n odd numbers is n squared, which is interesting. And it's hard to prove these sorts of things with the dots in the middle, which is one reason we're going to use induction. Here's another one like that. 1 plus 2 plus 3 plus, this time we're just adding up all of the numbers from 1 to n, the natural numbers. And the result here is n times n plus 1 over 2. Now that's a formula you may have seen before, but this is one we'll go ahead and prove a little bit later. Here's another kind. N is always less than 2 to the n. Now there are many ways to prove some of these statements, but in this section we're going to talk about proving them with induction. Here's another one. 3 to the n minus 1 is divisible by 2. Now, if you start thinking about these, you may wonder, how would I prove these? And you'll find out that induction is the ideal way to prove these. Now, in this unit, in this section, we will prove all 4 of these. Here is the theorem about mathematical induction, so we can start using it. Theorem. This is going to be called mathematical induction. And it's a technique that's been around only for a few hundred years. Pascal, the man who invented Pascal's triangle, or rather studied Pascal's triangle, was one of the first people to actually use induction correctly. So we'll talk about that a little bit later, because Pascal's triangle will be turning up later. But for now, mathematical induction, if a statement about natural numbers, because that's the kind of statement we're talking about here, if a statement about natural numbers satisfies both of the following statements, both, and I'll mark them here, Roman numeral 1, the statement is, it, meaning the statement, is true for 1. I'll box that in. So we have a statement about natural numbers. If it satisfies both of the following Roman numerals, the first is that the statement, our statement here, is true for the number 1. And Roman numeral 2, now this one is an if-then statement. Roman numeral 2 is if it is true for some k, so it's true for some k value, then immediately following from that, it is also true for the very next number, k plus 1. So if that always happens, okay, if we have that it's true for 1, and this result always happens whenever it's true for something, k, the next one immediately follows, then this theorem about mathematical induction says the statement that we were looking at originally is true for all natural numbers in n. So this is what it takes, if you want to use mathematical induction, to show that something is true for all the natural numbers in n. You have to show 2 things. You have to show, first of all, it's true for 1. And as I will say later, that's just a way of establishing that the statement is not nonsense, that it actually works for something. Then you want to show that whenever it's true for some k value, it follows that it's true for k plus 1. Now, I'm not going to prove this, but I'll give you the idea why it's true, because this is really the key to using this. Here's the proof idea. First of all, by Roman numeral 1, the statement is true at least for n equals 1. So it's true at least in the case that the n in your statement is replaced by the number 1. Then here's how the rest of the proof is going to go in outline. Since it is true for 1, by 2, applying Roman numeral 2, then it is also true for the next one. Also true for 1 plus 1. So we're adding 1 here, which is 2. Okay, now 2 is true. Well, since it is true for 2, again I apply Roman numeral 2 by Roman numeral 2 again, then it is also true for 2 plus 1, adding 1 again, which is 3. So I've established it for 1, that was part 1, Roman numeral 1, and then since it's true for 1, 2 allows me to take this trip to 2. But if I applied Roman numeral 2 to number 2, I then can get up to 3, and so on. Okay, I won't do this, but this takes you out to infinity. And that is the proof idea. The first part gives you an anchor in reality. The second, Roman numeral 2, gives you a way of going from the kth case, which in this case is 1, to 2. Down here, the kth case is 2 to 3, and so on. Now let me be sure that you are warned here. Warning. If you're going to apply this technique, both 1 and 2 must be satisfied for this theorem to apply, for the theorem to hold, or apply. Let's put apply down here. Okay? Both of those must be satisfied. You cannot leave one of them out because you can end up with nonsense in that case. So, if you're going to apply this technique, here is my recommendation on how to apply it. Okay? The proof by induction that you will want to use. Here's my recommended technique, and I will then illustrate it 4 times. First of all, show that Roman numeral 1 holds. This case is often referred to as the base. And as I said before, you can consider it an anchor in reality. It means that the statement that you're trying to prove is actually true in at least one case. Then write down, and this will be your assumption, write down the kth case, what it actually looks like. Sometimes this is called the induction hypothesis, but we can just call it the assumption. Write out the k plus first case. Why? Because that's your goal. That's what you want to end up with. You don't know yet that it's true, but at least you know what it looks like, so you know when you reached it. Then finally, proving the k plus first case is true. This is the heart of induction. This can and often must use the base or the kth case, which you've assumed, in your proof. But beware here of circular reasoning. Okay? The proof here is the hard part of the induction. And it'll be the part where you spend the most of your imagination. The rest of it is just setup. Showing 1 holds is usually easy, writing the assumption is easy, writing out the goal is easy, and then how to get from the assumption to the goal is the proof. And that's the part that is the heart of induction and the part that will take you the most effort. So with that in mind, let me go ahead and do an example here so I can illustrate what I just talked about. And my example will be what I call statement number 1 back in examples. And that statement, remember, was 1 plus 3 plus 5 plus ... up to 2n minus 1. 2n minus 1, of course, is an odd number. Adding up that many odd numbers, the first n odd numbers, is always equal to the number of odd numbers you add up squared. Now, there are different ways to see this. I want to show you how induction can help you see it. Proof. First, we'll do the base. The base is to see if this is true for 1. So I take my formula here, which is the form that all these numbers take, and I put 1 in. And so on the left, I get 1. And I ask myself, is that equal to 1 squared, which is the formula on the right? Well, that's true. Okay? So that means that Roman numeral 1 is satisfied in the theorem. Okay, good. I've established my base. Then I will write down my assumption. So I'll write assume. This will be the kth case. So 1 plus 3 plus 5 plus up to 2k minus 1 equals k squared. So I'm assuming that the rule works for some kth case. And I know that that's not a vacuous statement because I already know it works for k equals 1. Now, what I want to do next is prove the goal. As I named it earlier, I want to prove the goal, and here is the goal. Let's state the goal. 1 plus 3 plus 5 plus dot 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 plus, and I need to go to the next term following this. Now if you think of this as a box, as we've done so many times before, you'll see that the next term is 2 times k plus 1 minus 1 equals, and here this is another box squared, so that's k plus 1 squared. So using the box notation we've looked at so many times in this course will help us write the next term out. Sometimes it helps to simplify immediately. Remember, this is the goal. This is what you're trying to get to. You want to make it look as easy as possible so you'll know when you get there. So I will simplify this as 1 plus 3 plus 5 plus up to, and then I will see what this is a little bit more simply. Well, 2 times k will give me 2k. Then this is 2 minus 1, so I'll have plus 1 in there. And that will equal, and I'll just leave that as k plus 1 squared because that's simple enough for me. Now, when I do the statement below, I'm going to refer to this side as the left-hand side. See that abbreviation, LHS? That's fairly standard in many areas. LHS stands for left-hand side. Okay, this is simply a statement of the goal. Now, I'm going to do the proof of the goal. So here is the proof of goal. Okay? The left-hand side above, I'll rewrite it as 1 plus 3 plus 5 plus dot 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 plus. Now I choose to write the term before the last one also. 2k minus 1 plus the last one, which is 2k plus 1. This is the last term right before the k plus first term we worked out a moment ago. Now I'm choosing to write this out, and you will choose to do that very often also. Here is the advantage. Look, that we already know by assumption. This is k squared. And let me bring back the previous page so you'll know what I'm talking about here. We assumed that this number up to the k minus 1 case, 2k minus 1 case, was k squared. And that's what I've just used. I've just used that assumption right here. So continuing my equality, this becomes just k squared plus 2k plus 1, bringing the 2k plus 1 down. But now looking at this, I immediately recognize this. This is a case where you should recognize that this is k plus 1 quantity squared. And that's what I was trying to get to. I was trying to show the left-hand side equals k plus 1 squared. And now I have actually done it. So from this, I get that Roman numeral 2 is satisfied. And since Roman numeral 2 is satisfied, hence 1, which is the name of this statement, is true for all n in the natural numbers. Okay? Now let me remind you here, let me bring back the previous page. I had the statement on here, prove this goal. Now it may even pay for you to put a question mark there. And every time you state the goal, to remind yourself that at this stage I do not know whether this is true. This was my warning about circular reasoning. I don't know that this equals this. So when I start on the next page, I start with the left-hand side, and I only use previous information, and I hope to end up with the right-hand side. That's what I've done here. Left-hand side is just written out this way, and then I notice that the first part, by assumption, is k squared. That leads me to this, which I recognize as this. And that is what I was trying to get to. So finally, Roman numeral 2 is satisfied, and I'm done. So I wanted to warn you to be careful about the organization here. So on that note, here is a problem for you to try and mimic what I just did in organization and style, because this is very similar in difficulty to the previous one. Here is the one, number 2, for all n in n, go ahead and prove that 1 plus 2 plus 3 up to n is equal to n times n plus 1 over 2. That's what I want you to prove now. So go ahead and try that using exactly the technique I just showed you. And I'll come back in a moment and show you what I did. Now the first thing we're going to do is look at the base. Here is the problem again. Here is the statement I'm trying to prove. Add up the first n numbers, and I hope to get n times n plus 1 over 2. So the base case here, which is always easy to do, the base case is, how many numbers am I adding up on the left? Just 1, so that's just the number 1. My question, is that equal to the formula which says it should be 1 times 1 plus 1 all over 2. Now is that true? Well, sure it is. 1 plus 1 is 2, 2 over 2 is 1, so this is true. Okay, so that means 1, that part of the theorem, Roman numeral 1, is satisfied. Oh, good. We can move on. Assume, this is the kth case, we can just write this down. This is just recopying with k in place of n. So this is 1 plus 2 plus 3 plus up to k, and this is k times k plus 1 all over 2. So there we go. We've got the assumption written down. That's easy enough. Now we want to write down the goal, so we want to prove the goal. And the goal is this: 1 plus 2 plus 3 plus dot 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 plus the next number following k, which is k plus 1, is equal to, we don't know what's equal yet, but that's what we want to show. And then up here, if you want to remember this as box times box plus 1 over 2, then we're replacing the boxes, which are k's, by k plus 1's. So we will have k plus 1 here times k plus 1 all over 2. Well, of course, I can simplify that. And whenever you can simplify something, go ahead and do it. And I will have k plus 1 times k plus 2 over 2. Because if the goal is simpler to look at, it may be that I will find it more easily when I work with it. I want to know when I get there, after all. And I will refer to this entire left-hand side as the left-hand side again on the next page. And remember how the proof will go. I will start with the left-hand side here. I will use information that I know from up here, and then I will hope to get to the right-hand side. If I do, then I will have a proof. If I don't, then I've got something wrong. Okay, let's go ahead and see if I can do this proof. So here's the proof of the goal. And so left-hand side, now I'm going to rewrite that left-hand side as 1 plus 2 plus 3 plus, remember the left-hand side went up to k plus 1. I'm going to write in the term before that because I think that'll be helpful. There's the k, which is before k plus 1, and then k plus 1. Now, this was my choice to do that, but look what happens. I now recognize this as my assumption. By assumption, I know exactly what this is. By assumption, this is k times k plus 1 over 2. The first k numbers add up to this. And then I will just bring that k plus 1 down here. So now I have this expression. Well, now I just do algebra as it seems natural to do, trying to simplify things. I see the k plus 1 is common to both, so I will factor the k plus 1 out. What am I left with? Here I'm left with k over 2. Here I'm left with 1 because I factored out the k plus 1. Then I'm going to combine these into a single fraction because that also seems natural. And I will then have a denominator here of 2, a k on the top plus, and 1 I will rewrite as 2 over 2. So I'll have k plus 2 over 2, and now I begin to see what I've got. K plus 1 times k plus 2 all over 2. That is what I was trying to get to. So 2 is satisfied. Okay, we had to satisfy both Roman numeral 1 and Roman numeral 2. So now 2 is satisfied. And the short answer to the rest of this is that we're done. Because by the principle of mathematical induction, the theorem, if I've shown that 1 and 2 are satisfied, then I know that my statement is true for all n. So the statement, the original statement you were working on, this statement that the first n numbers adds up to this formula is now true for all n in the natural numbers. So that was a nice example, and I hope you ended up with something similar to what I got. Here's a new one. This was example 3 from before. I want you to try this on your own a little bit, and then I'll come back and I'll show you how to attack this. For all n in the natural numbers, n is less than 2 to the n. So you'll have to change your proof technique. It's not going to be a matter of adding things to one side and working with it that way. You'll have to think of another way to do it. But I'll let you struggle with that for a bit, and when we come back, I'll show you what I did. First, we'll start, as always, with the base case. Now remember the statement. The statement was, is n less than 2 to the n? So the base case is quite easy to check. Is 1 less than, I'll put a question mark there, 2 to the 1? Well, of course that's true. And so Roman numeral 1 is satisfied. So we're okay as far as that goes. We will then write down our assumption, which is the kth case. That's easy to write down also. K is less than 2 to the k. So we're on a roll here. We want to prove the goal. Well, the goal is easy to write down also. We want to prove that k plus 1 is less than 2 to the k plus 1. And there really isn't any way to simplify that any further. So this is turning out to be simple so far, but then the first part is really mechanical. All of this is something anybody can write down. The next part is where the thought will come in. So here is the proof of the goal. We know by assumption, so I'm starting a little differently here. I'm starting with the assumption that k is less than 2 to the k. Now I'm going to try and modify one of these sides to look like my k plus 1 case. And here's what I will do. I will multiply both sides, of course, by 2. If I do that, on the left I have 2k, and on the right I have, well, what's 2 to the k times 2? That's 2 to the k plus 1. So I've already established the right-hand side of an inequality. I need to somehow get k plus 1 down here in order to get k plus 1 less than 2 to the k plus 1. However, we observe the following, but k plus 1 is clearly less than or equal to k plus k. This is clear. There's no mystery about that. The k is common here, and k is greater than or equal to 1, so this side is always greater than or equal to this side. But what is that side? That's 2k. And that, we know, is less than 2 to the k plus 1 by this previous result. So look what we have. Let's take the first part and the last part. So that means Roman numeral 2 is satisfied. See, we've proven that k plus 1 is strictly less than 2 to the k plus 1. Now this took a little different kind of argument, but it wasn't very hard, I hope. And so once again, we're done. Because if you have 1 and 2 satisfied, then your original expression, which is here now, n less than 2 to the n, is true for all n in the natural numbers. So I hope that that wasn't too hard for you. Let me do one more, the last example I showed earlier. Now, this is problem number 4, the example I showed earlier. I wanted to go ahead and finish this off for you. This is a bit different from the others. And remember what it said, 3 to the n minus 1 is divisible by 2. So it's a statement that's a little bit different, but I think you'll see that the technique that we apply is the same technique as before. Base. Okay, the base here is the statement 3 to the 1 minus 1 is divisible by 2. Well, is that true? Well, of course it is. 3 minus 1 is 2, so that's easy to check as true. So that means that Roman numeral 1 is satisfied. Okay, that part was easy. We will write down the assumption now, as we've done before. And the assumption is this phrase, 3 to the k minus 1 is divisible by 2. Okay, there's that. That's always easy to do. And now I want to prove the goal, so I need to state the goal statement. Prove the goal. And the goal here is this statement that 3 to the k plus 1 minus 1 is divisible by 2. And we'd hope that we can prove that using some methods that perhaps we haven't looked at before, but should not be too hard to figure. Okay, let's go ahead and try that. Proof of the goal. And it will turn out that a simple observation will give us the entire proof, as you'll see. So 3 to the k plus 1 minus 1. That is what we would like to show is divisible by 2. Well, first of all, notice that 3 to the k plus 1 is 3 to the k times 3 to the 1. That's thus 3 times 3 to the k minus 1. Well, if you have 3 to the k's, you can write that as 3 to the k plus 3 to the k plus a third 3 to the k minus 1. But now observe that by collecting terms like this, we have the following. This is 2 times 3 to the k plus the expression 3 to the k minus 1. This first part is divisible by 2, obviously divisible by 2, and because it's clear, because it has a factor of 2 in it. The second part is divisible by 2 by assumption. So together they make this entire expression divisible by 2. But this expression, which I'll end here, this expression equals the original. So the original 3 to the k plus 1 minus 1 is divisible by 2. Well, so Roman numeral 2 of the theorem is satisfied. And therefore we are done and have shown that the original statement, which was back here, 3 to the n minus 1 is divisible by 2, is in fact true for all natural numbers n. All right. Well, I hope you've seen enough examples of mathematical induction now to get a sense of how it's done. We're going to move on now to our final topic in this unit and the course, the binomial theorem.